The industrial food supply chain relies on a specific biological assumption that when the ground freezes, the growth must stop. But surviving the winter requires understanding that soil is merely an anchor, not a requirement for life. In the 1600s, a Belgian scientist named Jan van Helmont set out to test exactly what a plant consumes. He planted a 5-pound willow shoot into a pot containing exactly 200 pounds of completely dried soil. He watered it with nothing but rain for 5 years. At the end of the experiment, the tree had grown to a massive 160 pounds. The soil had lost less than 2 ounces. This empirical data proves a central biological axiom. Plants do not consume dirt. They generate their physical mass from water and atmospheric carbon. The earth around them is strictly structural. Once you realize dirt is doing nothing but holding the plant upright, you can discard it and replace it with a highly engineered, efficient alternative. Traditional dirt farming wastes massive amounts of energy and resources. By abandoning it, we can build a decentralized, soilless system inside a simple closet. When you pour water into a backyard garden, up to 90% of it is lost. It either percolates deep into the earth, far beyond the reach of the root system, or it simply evaporates into the atmosphere. It is a thermodynamic failure. The ancients solved this by engineering localized waterworks. The Hanging Gardens of Babylon bypassed the arid earth entirely, using an Archimedes screw to lift thousands of gallons of water directly to suspended roots. We see similar agronomic control in the historical Chinampas of central Mexico, where early engineers integrated water flow directly into the agricultural beds, creating a state of constant nutrient availability. We can condense this ancestral engineering down into a $20 zero-electricity bioreactor, a system capable of yielding fresh tomatoes in the dead of winter. By taking the soil out of the equation, we remove the geographic limitations, eliminate soil-borne pests, and completely reclaim that 90% water deficit. The foundation of this decentralized system requires scavenging or purchasing a simple food-grade 5-gallon plastic bucket. This acts as our primary fluid reservoir. If the plastic is clear, you must block all sunlight from penetrating the sides. Light in the reservoir zone will trigger photosynthetic algae, which will aggressively compete with your plant's roots for oxygen and nutrients. To monitor the fluid level without disturbing the closed root matrix, insert a 1/2-inch PVC pipe cut to the height of the bucket and drop in a wooden dowel. This functions as a zero-electricity measuring stick. Next, we replace the dense soil with perlite. This is an inorganic, lightweight volcanic glass. You fill the bucket with these jagged pieces up to 1 inch from the top. Perlite holds an extremely high surface area to volume ratio. This physical property traps exactly the right ratio of liquid to oxygen, creating a perfect equilibrium of moisture and air. The core engine of this system is capillary wicking. The perlite actively pulls the water upward from the reservoir, creating an oxygen-rich, unsaturated layer at the top where the roots can continuously breathe. By relying entirely on passive fluid dynamics, we eliminate the need for expensive electric pumps or aerators. It is a self-regulating biosphere. With the structural mechanics in place, we transition to chemical engineering. To force rapid winter growth, we must supply the precise metabolic fuel the plant requires. Plants expend massive amounts of stored energy fighting their way through dense clay to search for isolated minerals. By dissolving highly bioavailable nitrogen, phosphorus, and potassium directly into the water, we bypass this labor. This visual represents our dissolved mineral mix. You want to measure your target concentration to maintain a strict metric between 800 and 1200 parts per million. You must also leverage the science of enzymes by balancing the pH. Using basic household additives like baking soda, you adjust the liquid to sit strictly between a 6.0 and 7.0 pH. This precise acidity prevents a condition called nutrient lockout. It ensures the roots can actively absorb the ionized minerals suspended in the water. When roots are suspended in this optimized, pre-digested chemical matrix, the plant accelerates its metabolism. Your winter tomatoes will generate biomass 30 to 50% faster than they ever could in soil. Because the roots consume the liquid directly from the closed reservoir, there is zero waste. This strict chemical suspension is exactly how we achieve complete thermodynamic water conservation. A bucket of perfectly balanced nutrients means nothing if the environment is hostile. To grow inside during a blizzard, you have to engineer an artificial summer. Standard kitchen lights lack the intensity for photomorphogenesis. While high-pressure sodium bulbs output high heat and specific spectrums, targeted LED arrays provide precise wavelength control at a fraction of the power cost. This chart tracks the electromagnetic wavelengths required for growth. Flooding the plant with the blue light spectrum, between 400 and 500 nanometers, specifically dictates the generation of heavy vegetative stems and broad leaves. When you are ready for the harvest in mid-January, you introduce the red end of the spectrum. Wavelengths between 600 and 700 nanometers trigger the biological clock to stop producing leaves and start forcing floral and fruit production. You pair this photonic control with a thermal circadian rhythm, maintaining a daytime temperature of 75 degrees Fahrenheit and dropping it to 60 degrees at night simulates the natural cooling period tomatoes require to set fruit. Finally, you add an oscillating fan. This creates mechanical wind stress, which induces microfissures in the plant's stalk. As it heals, it generates a physically thicker, stronger structure capable of supporting heavy fruit. By locking in the exact light wavelengths, temperatures, and airflow, you isolate your biological matrix entirely from the external environment. Once the fruit ripens, you extract the final and most valuable yield of the entire system, the genetic legacy of the plant itself. Extracting and preserving your own seeds severs your dependence on commercial agricultural supply chains. You control the means of production for the next cycle. However, tomatoes possess a specific biological defense mechanism. Every individual seed is encased within a clear, gelatinous germination inhibitor. Evolutionarily, this gel sac prevents the seed from sprouting prematurely while it sits inside the warm, wet environment of the ripe fruit. To bypass this inhibitor, you must use a fermentation process. You squeeze the seeds into a jar of water and let them sit for several days to trigger a controlled rotting phase. As a layer of mold forms on the surface, its enzymes actively break down the gel casings. This mimics the natural rotting process and ensures the seed is ready to awaken. Once the gel is dissolved, you rinse the seeds through a fine sieve to purify them, then leave them to dry on a plate. This resets their biological state, keeping their energy dormant until you are ready to plant. By continuously saving seeds from your highest performing plants, you are executing human-driven selection. You are engineering an adaptivar, a genetic line perfectly calibrated to the specific temperature and light parameters of your indoor matrix. Mastering this microbial extraction process means a single $20 investment yields a recurring, untaxable dividend of fresh nutrition. With a plastic bucket, an inorganic matrix, and targeted photons, we have successfully built a self-sustaining biological cycle from scratch. It requires no mechanical pumps, wastes no water, and thrives while the soil outside is frozen solid. It is the direct synthesis of precise chemical engineering and ancestral fluid dynamics. The author Michael Pollan describes humans acting as bumblebees for these plants, facilitating their survival in exchange for nutrition. We scale that concept when we build trade networks with our neighbors, exchanging these resilient, winter-hardy seeds. You can look out the window at a blizzard, turn around, and harvest a vine-ripened tomato in your kitchen. Independence starts in a 5-gallon bucket. By reclaiming the waterworks of our ancestors and applying the science of hydroponics, we break the seasonal chains of the industrial food system. Reclaim your backyard loot and join the resistance of the green thumb. Subscribe to Unearth the History for more blueprints on forgotten hacks and backyard engineering. Like this video if you're ready to grow your own nutrition, and share this $20 blueprint with a fellow disruptor. The ground might be frozen, but your garden is just beginning.